Just note down the first numerical on that. Just repeat this. A single phase semiconductor. A single phase semiconductor is operated from a is operated from a is operated from a 120 volts, 60 hertz supply. 120 volts, 60 hertz supply. Full stop. The load current with an average value. The load current with an average value. Load current with an average value. I suffix A. I suffix A. Average value. I suffix A. Average value IA. Continuous with negligible. Continuous with negligible ripple content. Ripple content. Full stop. The turns ratio of the transformer. The turns ratio of the transformer is unity. Is unity. Full stop. The delay angle alpha is equal to. The delay angle alpha is equal to pi by 3. Pi by 3. Calculate. Pi by 3. Calculate first bit. Harmonic factor of the input current. Harmonic factor of the input current. Second bit. Displacement factor. Displacement factor. Third one, input power factor. Input power factor. Yes, how we are calculated? What are the given data? Given data is supply current they have given. Sorry, supply voltage 120 volts they have given. With a firing angle of pi by 3, the average output voltage is equal to IA value. Then you know the formulas for harmonic factor, distortion factor, as well as there will be input power factor. You just substitute over there, you will get the values of HF. What is the formula for HF? Harmonic factor. Pi into, this is under root pi into pi minus alpha divided by 8 cos square alpha by 2 minus 1. Here, whatever the value of alpha you are substituting in terms of radians. You just set your calculation mode in radians and calculate the value of HF. Similarly, you have displacement factor. df is equal to cos of phi 1 is equal to cos of alpha divided by 2. Similarly, you have power factor. What is the formula for power factor? square root of 8 divided by pi into pi minus alpha into cos square alpha by 2. You have three formulas. You just substitute alpha value in terms of radians. That is pi by 3. First you need to calculate HF, DF as well as PF. What is the value of HF? HF becomes 0.3108. Then DF is 0.866. Then power factor is 0.826. the value of displacement factor 0.866, then power factor is 0.826. Then after that, just note on the next topic, that is on the single phase full wave converter. This is also operated with two loads, one is R load, another one is RL load. Actually, if you are connecting a diode, then how will the full wave rectifier diode will be like this, right? Output will be like this. But here we are connecting a switch is in the form of a SCR. We can control the voltage. Up to this, we are controlling the voltage, and the waveform it looks like that. Up to this, we are controlling the voltage, the waveform it looks like that, right? And up to this, we are controlling the voltage, the waveform will be looks like this. Same waveform here we are. What? Here you are already familiar with the operation of full wave rectifier circuit, right? When we connect the diode as the switches, right? But here we are replacing the diodes by SCRs. Okay? When we are considering as a full wave rectifier circuit, the output voltage I was already shown. Whatever the output you are getting, the output will be like this, right? For positive cycle, for negative cycle, for positive cycle as well as for negative cycle. Okay, that is you are already studied in analog electronic circuits, right? Full wave rectifier circuit. Same thing, whatever the output you are getting, that is we have to control. Then in order to control the output voltage, we are replacing the diodes by SCRs. Okay, we are replacing the diodes by SCRs. If you connect the diode, we will get the output voltage like that. Okay, then if you connect the SCR, we will get the output voltage of a controlled angle alpha. Okay, that is I was already said that if suppose consider if set for 30 degree, that is we can divide 0, this is 10, 20, 30, right? The waveform will looks like this. Okay, and similarly here 180, 190, 200. The waveform will be like looks like this. Same thing here we are drawn, that is from alpha to pi. Instead of we are representing 30, 40 or there will be a 50 degrees. Generally we are represented as alpha band. Alpha to pi and from pi plus alpha to 2 pi. Okay. Simple thing, you are already familiar with the operation of the circuit. Okay. As much as the semiconductor circuit. There in the semiconductor circuit you have two SCRs and two diodes. But in the full wave rectifier circuit or the full wave converter, you have four SCRs. Okay, T1, T2, T3 and T4. Okay, then during the positive, that is the input voltage is we are applying as a single phase AC supply. It consists of positive cycle as well as the negative half cycle of the supply voltage. During the positive half cycle of the supply voltage, the upper terminal is positive, lower terminal is negative. But here for AC there is no terminals, but for our reference we are representing as plus and minus. Okay. And or generally in case of AC we are represented as this is phase, this is as a neutral. Okay. And there will be a, whatever the current will be start going through the T1. The T1 will be triggered with a firing angle of alpha. Here you just observe that we are applying the gate drives of T1 and T2 at omega t is equal to alpha value. Okay, we are applying the gate pulses for the SCR T1 and T2 at a time. Okay, then that way SCR T1 is on, then the current will be start flows through the resistive load and T2. This T2 is also triggered at a firing angle of alpha. Okay, when both the switches will be in the on state condition, then the current will be start flows through the resistive load T2 and get back to the source voltage. Similarly, in the negative half cycle of the supply voltage, the lower terminal is positive, upper terminal is negative, right? Then the current will be start flows through T3. This is conducts in the negative half cycle of the supply voltage. Okay, because the negative cycle will be start from pi plus alpha. Okay, from pi plus alpha to 3 pi value. Okay, sorry, 2 pi value, right? This is SCR T3 as well as the T4 will be triggered at a firing angle of pi plus alpha, right? Then the current will be start flows through T3, resistive load, T4 and get back to the source voltage. Means when you operate both the circuit, you will get a positive output voltage. That's why we are drawn here that the output voltage alpha to pi is a positive magnitude. From pi plus alpha to 2 pi is also a positive magnitude. This cycle will be continuous until the circuit will be operated, right? Then the next cycle is 2 pi to 4 pi, 2 pi to 3 pi you have positive cycle, and 3 pi to 4 pi you have negative cycle. Okay? Then the instant will be start 2 pi plus alpha to 3 pi. Okay? T1 and T2 are forward bias. Then after that, the negative cycle starts from 3 pi plus alpha to 4 pi will get the output. Okay, and just keep it in mind when we connect the load is in the form of an resistive load. Whatever the nature of output voltage waveform we are getting is same as the output current waveform. Okay, because V is directly proportional to I. But if you represent the magnitude of I naught is equal to V naught divided by R. Okay, that is whatever the magnitude you are representing over there. I naught is equal to V naught by R. Simple by applying Ohm's law for that. Okay, then how we can calculate the average value for this? Average output voltage as well as RMS output voltage. Here you just observe that for the positive as well as for the negative side. Okay, the waveforms are similar, right? That is from alpha to pi. You have a magnitude of Vm, and from pi plus alpha to 2 pi you have a magnitude of Vm. Okay, so represent here as the magnitude as this is Vm, right? Then this is 1 plus 1 plus 1 plus 1. Then totally how we are calculating the average? 4 divided by 4. Okay, means whatever the waveform we are getting over there. For all the instants, either if you are considering a positive cycle or either if you are considering a negative cycle, will get the same magnitude. T integral from 0 to t V naught of omega t omega t, right? And here I just consider this t as only one cycle. Okay, only one cycle, because in the positive cycle is also we are getting the same magnitude. In the negative half cycle you are getting the same magnitude. Okay, then whatever the V naught we are considering, V naught is equal to Vs is equal to Vm sine of omega t. Okay, we are applying a sinusoidal waveform for that, right? Then V naught average is equal to 1 divided by pi integral. Now what is the limits here? We are considering only one half cycle. What is the total conduction angle of T1 and T2? That is from alpha to pi, right? That's why we are representing the limits from alpha to pi. This is Vs omega t, Vs of omega t omega, right? Then similarly, 1 divided by pi integral from alpha to pi. Vs is Vm sine of omega t d omega t. You just integrate that value. Vm divided by pi. Integral from alpha to pi sine of omega t d omega t. Right? Then this is equal to Vm divided by pi. Integral of sine is you already know cos omega t. Right? Between the limits from alpha to pi. Right? Then just substitute over there. Vm divided by pi. This is minus cos pi minus of minus plus cos. Right? Then this is Vm divided by pi. What is the value of cos pi? Minus 1. Minus 1 into this negative sign. Right? We'll get a positive value. Then the resultant thing is 1 plus. Right? Vm by pi into 1 plus cos alpha is the average value of output voltage when the full converter is operated with R. Similarly, you have to calculate V naught RMS. Similarly, you need to calculate V naught RMS. In sometimes they ask for 4 marks. There are an expression for V naught average or V naught RMS for a single phase full wave converter, or otherwise they'll ask with a neat circuit diagram and waveforms, explain the operation of single phase full wave converter, and also derive an expression for V naught average and V naught RMS. Okay. Similarly, you have to calculate V naught RMS. How you are calculating? What is the general expression for V naught RMS? Same 1 by t integral from 0 to t V naught square of omega t d omega t to the power of half. Or what is the value of V naught RMS? Vm into under root of pi minus alpha plus sin 2 alpha by 2 whole divided by 2 pi. Okay. The next you just write out with RL load. Same thing here, RMS value, right? This is V naught square, this is to the power of half, right? Then V naught RMS is equal to 1 divided by pi integral from alpha to pi. This is Vm square sin square omega t d omega t. Right? Then this will be equal to Vm square divided by pi integral from alpha to pi 1 minus cos omega t divided by 2 d omega t. Right? Then this will be equal to Vm square divided by 2 pi. This is integration of alpha to pi 1 d omega t minus integration from alpha to pi cos omega t d omega. Right? Then here Vm square divided by 2 pi. What is the integration of 1 omega t between the limits from alpha to pi minus sin 2 omega t divided by 2 between the limits from alpha to pi. This to the power of. Then this will be equal to Vm square divided by 2 pi into pi minus alpha minus what is the value of sin 2 pi? If you are applying upper limit pi minus lower limit pi minus alpha minus sin 2 pi. Sin 2 pi value is 0 minus of sin 2 alpha. Right? Minus of sin 2 alpha into minus value. Right? You will get plus sin 2 alpha divided by 2. Then the resultant thing is V naught RMS is equal to Vm under root of pi minus alpha plus sin 2 alpha by 2 whole divided by 2. Okay, that is the RMS value of the output voltage. After that, you need to calculate. You just copy this single phase full converter operating with RL. Here, the output voltage and output current waveforms are different. The continuous current mode of operation, the total conduction angle of T1 and T2. This much T3 and T4 is. This is continuous conduction mode of operation. That is This current is continuous conduction mode of current CCM, and similarly in this block ECM is continuous conduction mode. The waveform will be like this. So, what's reason here? First, simple thing, we are replacing the R load by R load, right? I was already said that when we connect the R load, output voltage and output current waveforms are similar. But if we connect the inductive load, the output current waveform is different from the output voltage waveform, right? Then you already know the operation of this during the positive cycle T1, R, L and T2 and get back to the supply voltage, right? When the gate drive pulse is applied to the SCR T1 and T2 from alpha to pi, at that time the current will be flows through T1, R, L, right? When the current will be flowing through the inductance, when the gate drive pulses are applied for the SCR T1 and T2, when the T1 and T2 are is in the on state condition, at that time the inductance charges or it will be stores the energy, right? Then the current will flows through T2 and get back to the source voltage, right? Then after pi, right? After pi, actually the supply voltage is 0, okay? But according to this, the SCR T1 and T2 will be in the off state condition, right? But there will be whatever the waveform here we are drawn from pi to pi plus alpha, okay? During the negative half cycle of the supply voltage, whatever the energy stored in the inductor, where both the switches T1 and T2 will be in the on state condition, by using that inductance voltage, the SCR T1 and T2 will be continuously conduct in the negative half cycle of the supply voltage. That's why here we are representing the total conduction angle of T1 and T2 is from alpha to pi plus alpha. Okay, that is from alpha to pi because of the supply voltage, and from pi to pi plus alpha, whatever the magnitude here we are representing, this is because of the inductance voltage. Okay, by using that inductance voltage, the SCR T1 and T2 will be continuously conducts in the negative half cycle of the supply voltage. Okay, then after that, for the negative half cycle of the supply voltage, T3 and T4 are forward bias. Okay, then at that time, once again the output voltage will start from positive pi plus alpha to 2 pi. This is the total conduction angle of the SCR T3 and T4 because of the supply voltage. Okay, but the supply voltage is 0 at 2 pi. But whatever the output voltage here we are shown from 2 pi to 2 pi plus alpha. This is because of the inductance voltage. Okay, because of the inductance voltage. Means the property of the inductance, when the supply voltage is applied to the switches, at that time the inductor becomes charges. Okay, and when the supply voltage goes to zero value, then by using that inductance voltage, the switches will be continuously continuous. Similarly, with respect to the current also, that is from alpha to pi, this is with respect to the load, or generally we are represented as an inductance current. The current will be starts increases when both the switches T1 and T2 will be on because of the supply voltage. Okay, then after that, whatever the energy stored in the inductor, it will be goes on reduces. When that inductance voltage carries the SCR T1 and T2. Okay. Similarly, from pi plus alpha to 2 pi, the inductor current will be increases, and from 2 pi to 2 pi plus alpha, the inductor current will be goes on reduces. Okay. Like that, the circuit will be operated when we connect the load is in the form of an inductive load. Similarly, depending upon that R load, if the inductance value we are designed for larger value, you will get the waveform like this. If the inductor we are designed for a smaller value, then the inductor current goes to 0. Okay, that is the way inductor current goes to 0. Okay, that is it will charges from 0 to maximum value, and from maximum to 0 value. This is whatever the deadline we are representing here. Okay, that is whatever the deadline here we are representing. This is represent the discontinuous or the discontinuous current. The waveform is not continuous. Okay, it will be a discontinuous current mode of operation. Okay, this is only happen only when if you are connect the load is in the form of an inductive. Okay.